space, and it's a powerful moment. It is not any other spaceship. Hubble touches people, it touches me.
This is the inside story of how the mission was planned, of what really happened in space, and of their efforts to bring the universe back into focus. It was soon after the telescope was launched that NASA admitted to a blunder.
The conclusion we've come to from that is that there's a significant spherical aberration appears to be present in the optics.
It was what a politician might call a techno-turkey.
It is not just mistakes, but it is how do you make a mistake. I make all kinds of mistakes, but I don't, and I fail all kinds of times. But it's critical to look at how you failed. And it is inexcusable the way they failed.
10 years before, by a simple mistake with a measuring instrument, the mirror had been ground to the wrong prescription. If anyone at NASA had checked it, they would have discovered that if light striking the outside edge of the mirror is focused here, light from the inside edge would be focused in a completely different place. So when they took a picture of a star, this was what it looked like.
Everybody was very excited by the sharp point in the middle, but the fuzzy blob worried me a little. So I used some software to try to understand in detail what was wrong there. It became apparent after a while that we were dealing with spherical aberration, and that really changed my life. I stopped doing astronomy and started doing optics in a big way.
Many astronomers didn't think they needed a manned space program, but NASA had insisted on designing this telescope to be serviced and repaired by astronauts. Almost anything on it, except the faulty mirror, could be replaced. Right from the start, they'd been intending to send up a shuttle about 3 years after launch, and were already due to improve on their original wide-field planetary camera, or WIFPIC for short, which had been designed in the 1970s. They would take that out and replace it by one with up-to-date technology. The original design had a complicated optical system in which the light was split in 4. It was at this next stage that simple mirrors could be replaced by a prescription that would bring the image back into focus. These new mirrors could restore near-perfect vision for this one camera, but that would solve only part of the problem. Space Telescope carries 5 scientific instruments. NASA's plan to replace the American wide-field camera did nothing whatsoever to help the other 4, which included the European Space Agency's faint object camera. Many of the astronomers who used Space Telescope didn't trust NASA to find a good solution. So an international strategy panel was gathered together and opened up to a wide range of scientists and engineers for their suggestions. The best arrangement they could find was to fold the path of light as it went into each instrument. They could make that idea work, but at a price. They would have to select and sacrifice one existing instrument in order to make space for a new box of mirrors that would correct the remaining 3, including the faint object camera. The moving parts would have to fit into a package no bigger than a shoebox, from which they could be deployed to within a 200th of the thickness of a human hair from its calculated position. The Corrective Optics Space Telescope Axial Replacement, Quasar, was delivered to the NASA cleanroom within 2 years, something of a record for NASA for such a complex instrument. Here, astronauts came to see the final tests of the intricate and delicate device that would fit like spectacles to correct Hubble's faulty vision. But the optics weren't the only problem. The telescope turns to point to each new target by spinning sets of reaction wheels, its gyros.
In the fall of 1990, we had one of our gyros fail. It turned out that there was a generic problem in 2 out of the 3 pairs of gyros we had on board. So immediately then we became worried about when would the next problem occur, and sure enough it did. I believe it was the following May. About 6 months later we had a second gyro failure. We finally had a memory failure at that time in one of the flight computers, so now our problems and our chores for the first servicing mission started to add up.
By the time the wide-field camera arrived at the Goddard Space Flight Center for its final tests, the plans for the mission were being subjected to review after review. This might look like a straightforward engineering checkout, but the astronauts who came to watch were in no doubt about the political pressure on their shoulders.
Enormous pressure, because it was very visible. People were having to operate in a very public environment. Everybody knew what happened back in 1990, the story of the failed mirror, and here NASA was trying to recover from that disaster, and so it was going to be front page news whether they failed or whether they succeeded.
I mean, there were words that were even such as, this is the measure of NASA. This mission is the measure. This mission defines, is there a NASA? Myself, I got most of the calls, you know, as payload commander. The calls and the letters. The more pressure I get, the more I dive into the details, the more I want to make this happen.
So they concentrated on their training for EVA, extravehicular activities, spacewalks, together with Claude Nicollier, the European astronaut who would operate the robot arm.
You get the J-hooks, grab the door, and as the person leans back and swing the door open, then face back down and grab the coprocessor. And that way you don't have to...
Meanwhile, the spacewalkers could work out what they would do when they were out on the end of the arm. They had demanded and got more intensive training than for any other mission. Above all, they had to be trained to work together as a team.
Stop. There we are.
What was different than in other missions was the intensity and effort that was made for integrated, so-called integrated training, including in a large water tank at the Marshall Space Flight Center, the neutral buoyancy simulator. We had the mock-up of the cargo bay of the telescope, and we had also a very high-fidelity immerged arm remote manipulator system. I could work at the control of the arm together with my two colleagues in EVA suits outside in the basin, and we could do a lot of integrated training, which has not been done so far to that extent for previous missions.
But there's a second equally important use for the tank and its control room.
Most wartime is usually development, not so much training. It's development, it's verification, it's test. And a lot of people don't realize that. They think we're just training. We're not training, we're trying to work it out.
They're developing what's called a timeline, creating, checking and rehearsing a series of coordinated actions in order to list them and add up each minute that everything they do will take. The buoyancy of water is the best simulation they can find for how they'll float in space. But in other ways, it must be completely wrong.
A lot of things that we do in the water tank we know are not right. For instance, moving the big masses around. You can weigh them out and you can get them neutrally buoyant, but you're still pushing around a lot of water, and you know that that's not the right way to do it. So in our training, we decided not to do that. We would have the divers do it for us, because that's negative training. You're training yourself to do exactly the wrong thing.
To move them a bit more realistically, they transferred to an air-bearing floor. The 880-pound CoStar box will float at the fingertips of Kathy Thornton. She must guide it into the telescope with just this much clearance. But neither here nor in the water tank is there any real match to what happens in space.
It is only imagination which now puts you in zero-G and puts you floating in your suit and puts the instability, the total freedom of motion that you get in zero-G, which you don't get in a water tank. Only imagination gives you a high-fidelity simulation.
And only imagination can tell them what extra tools they might need for all the things that could go wrong. What they do know is that the only one of the shuttles that would give them enough time in orbit hasn't been made available. To do everything, they've been allowed just 3 days. And now they've discovered that one task alone will take more than one whole day. So they've come to check that out. The power-producing solar panels up in space warp periodically and shake the whole telescope. So they'll have to take up and fit replacements which have thermal shielding to protect their supports from the sun. This task was already on their list, along with this visit to England, Bristol, to see them under test. But then another failure on the telescope increased the pressure on them yet again. For Hubble's magnetometers, the only available accurate model was in a Washington museum. This was Lockheed's original engineering mock-up, and it's 4 stories high.
Well, it really is pretty big, and we have here a full-scale model of the telescope. We have the top end as well as the bottom end, and that means that when the astronauts wanted to work on the magnetometers, which are the very top of the Space Telescope, then it's to the Air and Space Museum that they came to do that work.
When the telescope has turned to each new target, it's made absolutely steady by interaction with the Earth's magnetic field. So magnetometers to measure the field are essential. The old ones wouldn't be taken off. Instead, the astronauts must bolt new magnetometers over the old. Even so, the extra time that took and the sheer number of other repairs just grew and grew.
About 18 months ago, we began to realize that the amount of work we had to do at that time was exceeding the 3 EVA days we had originally envisioned doing the mission in. And that was before we had a failure of the solar array drive electronics and the decision to actually change out a second magnetometer. So we had 2 other things that come up on our plate after that.
We had an arbitrary timeline that says we can get it all done in 3. It wasn't a valid timeline, but people were afraid to ask for more than 3 because they were afraid it would get split up, or that the mission would get cut back, or someone would be afraid they're asking for too much, those kinds of things.
Well, there was a lot of pressure to divide the repair mission into 2, and in fact the NASA administrator himself was asking some very hard questions. Was it better to have 2 shuttle missions instead of 1? Try and divide the work out a little bit and take some risk out of the program by that method.
It was a fear of failure.
And we were pretty much opposed to that. We thought you ought to go for it.
There was just one way they could go for it. To get the 2 extra days they needed would demand one particular shuttle from NASA's fleet of 4.
The program did not want to commit to a single orbiter, because obviously that has less flexibility than saying we can fly on any orbiter that's available when it comes time to fly. But I pushed very hard to commit to Endeavour because of the additional tanks for the oxygen hydrogen, for electrical power for longer and longer number of days, and also for oxygen and nitrogen to repressurize the airlock volume after you've done an EVA.
T-minus 2 minutes and counting.
To me, to go up there with half a load, or to go up there with a full load and not attempt to do everything, would have been terrible. And the only reason we would not do that is a lack of courage.
5, 4, 3.
And NASA is a place you ought to have courage.
And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
The astronauts and engineers had already won their first victory. For this one mission, they changed the NASA system to get the shuttle they wanted. But to achieve that, they'd had to keep as close as possible to the launch date they'd planned over a year before.
That I'm proud of. We not only set the target date, we set what we were going to change out, and and that grew, as you know, and we were able to do that and manage money carefully, so we did it within budget, and we met the original schedule date.
In high orbit, they chased after Hubble. Now with a full 5 days and a couple more to spare in case anything did go wrong. But if it did, that could be bad news for the astronomers below, who were still using the telescope.
Even as the astronauts were up there, we were frantically taking data because that was our last chance. I mean, who knew whether when we'd get this opportunity again? Of course, there's also always the possibility something will go wrong and we won't have a telescope anymore.
We're a contamination threat. We can bang something. We are a threat. And so you recognize that. I'm a threat to this telescope, and I want to minimize that threat with quality of work. And that is a minimum of touch.
They matched orbits with the telescope.
It looked like a jewel. He discovered with this reflective material, which was such that already at a large distance we saw it as a very bright star becoming brighter and brighter. Then we used binoculars and we could see the detailed structure of the telescope.
We saw the solar ray that appeared to be bent, and we were kind of expecting it, but nobody could tell us for sure what condition it would be in.
And Houston, it's really big.
Endeavour, you've got to go for capture.
Dick Covey, Endeavour's commander, eased the shuttle beneath the telescope to bring it within range of the robot arm.
At some point I told him, it's okay, I can go and grab it. I started to move the arm, and just at that time there was a sunset. So the illumination conditions changed drastically, and suddenly I couldn't see anything from the camera that is at the tip of the arm that had to be aimed towards the targets. And there is a small floodlights that illuminated weakly the telescope, and I had to continue doing the grapple in these conditions. It was a tense moment.
Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
Please copy that, Covey, and there are smiles galore down here.
It's a big relief. So for the next 30 seconds or so, we didn't do anything else but cheer.
First objective accomplished. Now they can look forward to what their 5 days of spacewalks will hold, mostly inside the telescope, a daunting list of 10 items to replace. EVA Day 1. They go out in pairs. Jeff Hoffman joins his payload commander to take the first, third and fifth days. They're the odd couple. And now they'll see how the reality matches up to Story's imagination.
Going out the door, it is just awesome. I mean, it is flat frightening. And being scared doesn't hurt. Scared is good. And I was scared. I was scared pre-flight and I was scared in flight. Just flat scared. I was really afraid of surprises. If you look at the history of spaceflight, it's all surprises. I mean, what does come off according to the plan? I was afraid of a surprise that would jump out and I didn't have a good workaround. A showstopper that would just stop us cold in terms of the whole flight plan or for a given instrument.
Of the 3 tasks for the first day, they'll start with the gyros. They're inside here and require 2 new boxes called rate sensor units, RSUs, without which the telescope would soon be useless, unable to point. But when Story pulled himself right inside, he found that he couldn't turn his head to see what he was doing.
I've heard and I've seen in other reports where the flight helmets are more, they encroach on your vision more than the ones we have in the water tank. This field of view that you have here, that's one thing. But the other thing, the geometry of where I was in there versus where the RSU was, the geometry may have been different. But I ended up only having one of those shoehorns, and I had to guide the RSU onto that part and then feel for the other shoehorn. I couldn't see it.
But when at last he'd done that, the next problem was getting the door shut.
So we're out by about 1 centimeter. Copy.
Even the slightest chink of light or heat from the sun could affect the instruments. Leaving the experts on the ground to think about that, they moved up to some smaller equipment bays to change out 2 further control boxes for the gyros and replace some fuses.
Thanks, Jeff.
They were now ahead of schedule. Though it's difficult to keep track of time when you're going round through the night side of Earth every 96 minutes.
Getting dark out of it. Putting the lights on. Hey, lights on, visors up. And turn it down.
Time to get back for another go at the doors, for which their advisors down below thought they had an answer.
We would like to have EV1 go to the base of the telescope and pull down on the right-hand door using what you can estimate to be 25 pounds of force or less, using your calibrated muscles, I guess.
I've got the top one in. Hey, Story, do you have the handle latch closed? I'm about to. But wait a minute, the bottom one isn't coming right. We got to go and work on that.
We had not had experience with misaligned doors, and so that's something we had to learn up there.
It looks to me like if I'm just doing it at the top, I can get them to come together. So let me do that, and you hold the bottom. Okay, I'll go down there then.
But what the experts on the ground have told Story to do would need 3 hands, so he's none too happy.
Don't you want me to sit down and... I do. I want you to do the bottom, Story. Yes, Jeff, I'm a free floater. You know, it takes me a while to get out. I realize that. Okay.
So that wasn't working. Story now wanted to get a heavy-duty tool that he calls a come-along.
The ground, they took a lot of persuasion to do that, and they were probably thinking this come-along is good for 1,200 pounds force. I only wanted it for 5 or 10.
In Houston, if you copy, Jeff's just working, putting the doors back together and thinks he's found a way that seems to close the gap, and we're going to try that, if that's okay.
Mission Control finally gives way to the astronauts.
Press on, Tom. If you've got a way to do it, do it.
Once I got to go for the come-along in 5 minutes, we had the doors closed. There was a real change then, and the change then was, hey, just let them do the work up there. They are there, and turn them loose. If we run into something in the future, tend to let them go do it.
Endeavour Houston.
Go ahead.
Not to get you spun up, but we have 6 good gyros on the telescope.
Feeling they were ahead of the game, Story and Jeff moved on to make a start on a task originally scheduled for the other team.
We tried to stay busy. If we finished a little bit early one day, to do what we could to give the next crew a little bit of spare time on the following day in case they encountered some kind of problem we weren't expecting.
They'd been warned to expect a 50-50 chance that when the old solar panels rolled up, there could be a problem. This one's okay. But one support on the other is badly bent.
The fear was that it might break and then we would have things floating around. That's what we want to avoid. We had some criteria that we knew if these criteria were met, we had to stop it. Like if there was significant looseness in the blanket during the retraction, we had to stop it. And this is what happened. When that kink came close to the place where it was going to be swallowed.
So 50-50 was exactly right. And there was no place to stow the broken one, so that's a job for the following day. Tom Akers and Kathy Thornton had been trained to deal with that.
I remember hanging in the airlock thinking, it's just like training, it's just like training, it's just like training, telling myself, you know, not to get excited about this, that it's going to be so similar to our training I won't even notice it. As soon as you get your head out and start to work, you concentrate so much on what you're doing.
What they had to do first was disconnect the broken array. And for that, she must wait for orbital night.
We break the electrical connectors in the dark because the solar panel is still producing electricity. And we like not to break connectors when they're hot.
KKT, I'm letting go.
I love it.
You have it.
Where's the cake?
I'm not sure how long we waited for sunrise for the jettison, because I really have no concept of time out there.
When you're happy with the lighting, we concur you've got to go for release.
Okay, understand we have a go for release.
Okay, KT.
You ready?
Yeah, I'm ready.
Okay, they say you got to go for release. Expect 20 pulses.
I didn't throw it overboard, as some people think. I merely let go of it and was pulled back away from it.
The array just stayed there, it was rock solid, didn't move at all. After that, Ken Bowersox, the pilot, had the task of separating the orbiter from the solar array, but very, very slow. So we could hear all these jets make boom, 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 and then the orbiter moved very, very slowly away from the array. And after a while, SOX used the normal jets, and the gas from these jets went directly into the arrays and started to spin and flap like a huge pterodactyl bird. It was really spectacular.
Like a bird, Tom. Look at it.
I had a view of the Earth below me and the solar array flapping, and nothing else. I couldn't see the arm behind me, I couldn't see the orbiter, I couldn't see any part of me. It's like, you know, I was a consciousness alone in the universe with this solar array flapping over the Earth. It was magnificent.
The array will eventually burn up in the atmosphere. Back to business, and a new solar array is floated out, a mass of 330 pounds.
Moving the big masses around is It's the way you would expect it to feel intellectually. You know that it doesn't have any weight, you know that it has mass, and you worry about inertia, and you don't put any rates in that you can't take out. And you know that, you can understand that, but you've never felt it before.
Actually, when I crank a little on it, it floats up on its own. It's floating up, Story. You see that? Yeah. I just kind of barely started moving, and it keeps going. My hand on. I mean, you can just take it in, KT. Real slow. Go slow.
And ship's time, that's the end of the second day. The mission commander says so.
We had a lot of long hours and intense days, and when Cubby said it was time to go to bed, it was time to go to bed. And he covered the windows and sent the kids down to the middeck. With 5 of us sleeping down there, it was pretty cozy.
On EVA Day 1 and 2, we had taken care of the brain of Hubble and its power system. Now we had to go into eye surgery.
By replacing the wide-field planetary camera. First, Jeff and Story must ease the old one out.
Oh, fingertips. Fingertips. It just floats out. Lovely. Okay, Quad, let's move. Move away. Move away. 6 inches. We're clear. You got it. Now get out and look at the cavity. Roger, Storm. Okay, Quad, and now we have to go down to put this baby away. Okay.
They just hung that over the side while they took the new one out of the box.
Oh, look at that baby. Beautiful, spanking new with Hey, I can see it sliding up the rail. Yeah.
If it survived the rough ride into orbit, the greatest danger now will be to a tiny projecting mirror when Story takes off that cover.
Taking a mirror cover off, if you touch the pick-off mirror, whatever you leave on it, that's it. You leave your imprint on the pictures for eternity.
Down on the handle.
But it turns out when I went to do that, I didn't think about consequences. I went and did it because I'd done it hundreds of times. Every time you gave me a mirror cover to take off, I would do it 100 times until someone hauled me away and said, Story, you're going to wear it out if you do it anymore.
Great job, Story. All clear.
Getting that mirror through the orifice, getting that mirror inside far enough where it was protected not to make contact with anything as long as you maintain the attitude of the handrail outside. Now that was another critical moment.
It's a 1.5 in the hole. Okay, let's just keep it coming. You've got control left and right now. Yes, I do. Going in nice. Real nice. Looks like it's in there.
Next, a magnetometer. They'd last seen that in a museum. Jeff installs the new magnetometers as rehearsed by clipping the replacements on top of those already there. But then he spots a potential future problem with one of them.
You say you did get the MLI in the trash bag, Jeff?
Yes.
Okay.
The insulation protecting it from the heat of the sun had peeled back.
It was sort of sitting about like so. And when I touched it, it just flipped up.
While they sleep, the people down below will have to think what to do about that. But on day 4, they must move on to Quasar. To make way for that, Kathy and Tom must take out a healthy instrument that's unique to Space Telescope. It's called a high-speed photometer.
Intellectually, I knew it. It was going to happen, of course, but it was somewhat more of a downer than I had expected when it was actually happening. I had no real problem with that decision. It was a sensible decision to make, that we would be the sacrificial lamb. When it actually happened, though, emotionally it was a certain amount of sadness associated with the event. I guess probably because it indicated for sure that we were never going to be able to show the performance of which the instrument was capable.
For Quasar, this will be an almost exact rerun of what they were trained to do, both in the water tank and on the air-bearing floor.
Okay, KT, I'm getting ready to take it off. You have it? I have it. Okay.
That's where the mirrors will slide out from.
It's a very big box going in a very small hole with about an inch of clearance as we cleared the aft shroud going in, and then obviously the clearances got tighter because it had to be optically aligned. My concern was that we didn't have a chance to fit check something like that before flight. We always learn things when we do a fit check, and it would just kind of cross your fingers, hope things were built according to the way the drawing said they were built, that no changes were made after the drawings, and that the thermal environment it was in hadn't changed anything.
They've managed to close the doors on Quasar, and now with all their tools tethered, they're moving up a level to upgrade Hubble's computer. They're plugging in a 386-based coprocessor, which won't impress computer buffs, but it's a distinct improvement on the original 1970s technology, in which one of the memory chips has failed. Then, on the word from Houston, they become hunter-gatherers, foraging for heat insulation materials. They've been sent up a fax on how to make a cover for the threatened magnetometer. They hand over their bits and pieces to the evening shift, Claude and the pilot Ken Bowersox.
It wasn't a terribly skill-intensive job. In fact, the best training I got was probably cut and paste class back in kindergarten. It was really rewarding to be able to do something that allowed me to put my mark on the telescope.
Endeavour Houston, more good news. Coprocessor is checked out, fully verified.
So far so good, but there's still one day to go.
Good morning, Houston. Thanks for the Swiss music. I'm missing my iPhone.
EVA Day 5. And this is SADE, the Solar Array Drive Electronics. In a fit of cheese pairing when the telescope was built, NASA had cancelled the requirement that SADE could be replaced in orbit. Now Story must do just that.
I knew what it was going to be. It was my nemesis. That was my challenge.
I have the door.
It was not designed for EVA, and that's the thing. It is not EVA friendly. It was not designed to be changed out. So that's what I'm dealing with. I'm dealing with screws that the head is 1 millimeter to 2 in diameter. I'm on the end of a 60-foot arm that's bobbing around. I also didn't have any light. I have to focus right on that screw, and these lights you see are going by it. I need intense light to get that job done. But the big problem, and this is somewhat my fault, my imagination didn't work hard enough.
It's like doing brain surgery in boxing gloves.
If you hold the screw in and back it off, the part that has no threads, that will be riding in the connector, and therefore the screw is captive. The problem is in 0G, the screws dance. I know 0G. Everything dances until it's gone.
The screw is gone. I did not see it. Oh, I heard your story.
The one that got lost that we went chasing after and Jeff grabbed, that was the first one that told me, aha, these screws are not captive. And we chased after that one.
And it was spinning, so every second or so I could see it very, very bright in the sun, then it was a little fainter, then it was bright again, so I could easily spot it coming down the cargo bay.
Do you see it? It's down below.
It's coming down toward the payload bay. Claude's going to bring you down to it. Take it easy. Take it easy.
Take it easy.
I take you down slowly, Jeff.
It's coming down pretty fast.
Yeah, he's going to catch up with it.
Without even thinking about it, I did a proper motion to follow the motion of the screw, and we could catch it before it hit the cargo bay.
I have it.
Okay, arm stops.
Not a big problem if it had happened. We would have lost that screw, but the problem is you never know where this screw goes, and with Murphy's Law it could go to the worst possible place and prevent closing of the cargo bay doors or something else like that you don't want to happen.
They could at last move on.
Endeavour Houston, the GHRS is ready and awaiting.
Their 10th task, the Goddard High-Resolution Spectrograph, another scientific instrument, has trouble with its power supply. They could fix that by strapping a jump lead and relay box around it. But then there's an unexpected bonus for Story.
When Jeff and I went up to install the cover that we had manufactured to cover the magnetometers and rose up right to the level of the aperture door, the top, and then I was able to lean forward and get a little more altitude. And I'm looking above the telescope now and down onto the west coast of Australia. And so I'm 18,000 miles an hour, 25,000 feet per second at 370 statute miles. And there is absolutely nothing but a wide panoramic view of the Earth and the entire continent. From this altitude, you can see thousands of miles. I had never experienced that kind of scale, which I am not Superman, but when you feel the sort of the urge to stretch out and fly when there is nothing there before you. As a human experience, I would have to say that that was the crowning moment. Mission Control was stunned. All they could say was the view, Story, the view.
Subject to the entire continent of Australia from here.
As ground control got Hubble back on its own power supply, they were still out to watch for any problems. All of the scheduled repairs had now been made, and within the 5 days they'd calculated.
There were a lot of cheers inside the cabin of the orbiter because we had accomplished what we were supposed to accomplish. We had fixed the Hubble Space Telescope.
The aperture door, Space Telescope's lens cover, opens up for business. And the robot arm lifts the telescope away.
This was another memorable moment, a very joyous moment. The release in itself is not a very difficult task, although it's critical. There is no margin for error. I released it with the arm. I had to move the arm sideways in order not to be too close to the high-gain antennas. At the time, Bowersox was going to do the separation from the telescope. There's a movement with the arm, and then it's up to the orbiter pilot to do the separation from the object that you're going to leave up there. The repaired, refurbished, and refocused Hubble Space Telescope.
Houston, we have a good release.
So now they can think of packing up to go home, knowing that they'd also accomplished NASA's second mission objective, to demonstrate that men and women can perform complex tasks in space, essential to a far bigger project than this, the space station to which NASA has linked its future.
If this had not gone well, I think it's, at least the conventional wisdom has it, that the space station would have been in very big trouble, because how can you build a space station in space if you can't repair a satellite that had been designed to be repaired in space? Now that they've shown they can do it, that's necessary, but whether it's sufficient to restore enthusiasm for space station, to restore NASA's image in the public mind, I don't know.
Whether it's out of the wood will be, I think, determined by the next time there is a serious failure and how the public and the media and the White House and the Congress responds to that, because such failures are bound to happen when you go for high-risk operations such as NASA goes for.
2 weeks later, it's the middle of the night at the Space Telescope Science Institute in Baltimore, and the wide-field camera astronomers are waiting for first light to see whether Hubble will at last deliver sharp, detailed pictures of the universe.
Hey! One to the right there! Oh! Did it! Wait.
Oh. No, go.
Yeah, let's get started. Bring it up. Yeah, bring it up.
Bring it up.
Come on.
Oh.
Come on.
Not bad. That's it.
bad.
There you go.
But Chris Barrows is still a little worried.
I was nervous because I knew there could be a lot of possible errors that we'd made in trying to understand the aberration. And I wasn't sure, even though we obviously had a much improved image then, I wasn't immediately certain that we'd really had fixed the problem.
There's an underlying smear. It's not quite in focus yet.
It needed some analysis and some further tuning of the mirrors to be certain that we were in good shape.
But plainly they were getting pictures.
Okay. That is better than any deconvolution you've ever seen.
Yeah. Those are actually stars.
Those are really stars.
I think we got it.
I think you got it.
Yeah.
Yep. Yep.
Sir. Maybe a little premature, but I'll shake your hand.
On the other camera, a few days later, just after Christmas, the first co-star mirrors had been deployed to produce their new corrected image of a star that's as good as if the telescope were perfect. With the European faint object camera, they could now make a direct comparison.
So the before and after is this one versus this one.
So they can now do real astronomy on a supernova, a star that's blown itself to pieces. Before the fix, it was fading away behind the smear from bright nearby stars underneath which they're trying to see an expanding cloud of debris. And there it is.
So would you scale it?
With the improved picture, they'll now be able to follow its progress.
And that's about as dramatic as it gets, obviously.
199 is what the...
Down in the observation room, more and more faint object camera pictures are coming in.
So that should have all this area covered with stars, if we're right, because it's a half an hour exposure.
The image was built up in the onboard computer and then transmitted in a single burst to the ground.
Ah, that's perfect, perfect, perfect. They're just perfect. Oh, wow, look at that. Nice and clean.
In this heart of a globular star cluster, they'd already shown that it's not held together by a single massive black hole.
The stuff that we had before. These two are blue stragglers. All the bright objects are blue stragglers.
What they'd never seen before is a whole lot of faint dying white dwarf stars. And hidden in there may also be lots of mini black holes.
Because you're now looking at a different population of stars.
Look at the dwarf.
The wide-field camera team, too, were now getting even more spectacular pictures, but so far had been kept well away from the press in a university basement until they'd checked the effects of the fine adjustments to their camera's internal mirrors.
The realization that it was fixed was slow in coming, but I think I really realized it, or emotionally realized it, when we saw these spectacular images start to come down of 30 Doradus, M100, Orion and so forth. Those images are so clear, so crisp, they're almost three-dimensional. And you can almost look at them and see what's happening in some of these objects.
Just 5 weeks after the fix, the United States senator who'd once called the telescope a techno-turkey was invited in as NASA's honored guest.
Good morning and welcome to NASA's Goddard Space Flight Center.
A political photo opportunity. The senator could now tell the world,
the trouble with Hubble is over. We have here a picture taken of the image of a star with the new faint object camera. And this is only the beginning. This is the picture taken of a galaxy in Hubble 1. It looks like the way you would look at a road map New Year's Eve. And this is what the new 1994 wide field planetary picture will show us. The pictures are remarkable. We will now, because of the Hubble fix, be able to do 21st century science. I believe these pictures are tangible evidence that not only has Hubble been fixed, but NASA is well on its way to fix that culture that created some of these problems.
That's enough politics. The reporters want the people who actually got those pictures.
Hey! One to the bright
Right there!
Bring it up. Bring it up. Come on.
When we saw this image, we already knew we were much better, and it certainly looked as if the defects in the image that we saw with this first light image were the sorts of defects that we could correct. And that indeed has turned out to be the case.
For astronomers, the significance of this improvement in the picture is that at an estimated 40 million light-years away, it will for the first time be possible to take measurements on individual stars in that galaxy that will help to calibrate what's called the distance scale, and with that determine the age of the universe. Nice picture. So, was it all worth it? Well, it's not just that one picture. The next day, it was astronomers who had a chance to judge for themselves. At a major conference, a lot more new pictures were on show for the first time. Observers and theorists will have so much more to work on, seeing deeper into the heart of this active galactic nucleus with its almost certain black hole.
It's wonderful. It's just what I've been looking for the last 20 years on this project. What I'm seeing in these pictures of Orion, as compared with the earlier Space Telescope pictures of Orion, is a gain that's just as big as those pictures were to the ground-based images.
In this nebula, a gassy star-forming region, they show much more detail of the places where stars will soon form. And 1,200 astronomers want to hear more.
Ground-based image, speckle image, we pick one image.
Compared with what can be done from the ground, Space Telescope will reach into 1,000 times greater volume of the universe.
So how it is that you manage to get...
The astronomers also hear how the new wide-field camera is now getting far better images than it could have before, even if the mirror had been perfect. Its vision now extends far beyond the colors of ordinary visible light. Here's a new light on a gigantic stellar eruption. So December 1993 may mark a giant leap in astronomy. But the pity of it is...
Well, we should have had this in 1983, shouldn't we?
Well, yes, if NASA had been able to keep to its original schedule, which was way beyond its powers at that time, and if, under its previous ownership, this factory had delivered a perfect mirror, which it neglectfully and ludicrously failed to do. There's a sting to the tale of this story. To be on the safe side, NASA had commissioned a spare mirror from a rival manufacturer. It was delivered here to the prime contractor, where it's been held under lock and key, hidden within its box for some 10 years. If it had been fitted to the telescope in the first place, they could have avoided all those lost years of astronomy.